In this video, we'll introduce gases and start looking at gas pressure. When we're looking at our three states of matter, gas is one of them. So far, we've been focusing on either liquids or solids. Remember, solids are when our particles are packed closely together and they cannot move freely. Liquids, on the other hand, the particles are still packed closely together, but they can move around. And then now when we're looking at gases, gases are very different because the particles are very far apart from each other and they move around freely where the gas will fill up the container that it's in. And looking a little closer at comparing our gases to our liquids and solids. Gases have a volume that changes significantly with pressure, and that's because of all the empty space between the gas particles. Solids and liquids, their volumes do not change with pressure. A gas volume can change significantly with temperature. So a gas will expand when heated and shrink when cooled. This is why we don't want to heat glassware that's sealed. The gas will expand inside the glassware and cause it to crack and break. And the volume can change up to 50 to 100 times greater for gases than for liquids or solids. Gases can flow freely. In fact, they can flow very freely. Gases have a relatively low density compared to liquids and solids. And again, that's because of all the empty space that exists with our gas. The gases have a relatively low density when compared to liquids or solids, and that's because of all the empty space between the particles in the gas. And then gases, when they form a solution, they can always form a solution in any proportion, which means gases are freely miscible with each other. You're not going to end up with part of the room over here with an extra amount of oxygen and over here with no oxygen. It's going to be distributed evenly throughout the room. Now, looking a little closer at temperature and density and how that affects our gases. We know all gases expand when heated. And this is because of an increase in the molecular energy of the gas, which makes them move faster, collide harder, and spread out further. So when we have warm gas, they're moving around a lot faster. So they're moving around much faster than our cool gases, which move slower. So we want to compare a warm gas to a cool gas and figure out which one has a greater density. Just by looking at our circles here, this is our area, and we can see in the cool gas, I can get 4 molecules in that area. In the warm gas, I can only get 2. So that means the cool gas has a greater density because I have more matter or more mass per area. And so now before we really get into gas pressure, we got to think about what pressure actually is. So pressure of a gas is the force of collisions with the container. So we really think pressure of gases is the force of the molecules colliding with whatever is around it. So if we have a container and a wall, our gas will bounce and hit the wall and exert a tiny bit of pressure right here. And then the gas will move away. A next gas particle will move, bounce against the wall, exert a tiny bit of pressure, and move away. So this is what gas pressure actually is. It's the force of these collisions against the container wall. And so we can really think pressure equals force divided by area. So gases in the atmosphere will exert a uniform pressure on all surfaces, which means if we're standing here, our gas particles are bouncing and colliding with us to exert atmospheric pressure on us. So that's all atmospheric pressure is the gas particles colliding with us. So we're getting bombarded by gas particles all the time. And the more gas particles, the more collisions there are with us, the more pressure we feel. So if you're here at sea level, you're going to feel a lot more pressure and get a lot more gas particles colliding with you than if you're up on top of Mount Everest. There's not as much atmospheric pressure on top of Mount Everest, so there's not as many gas particles colliding with the people up there. And so the way we measure this pressure is we typically measure it in PSI, or pounds per square inch. Another way we measure atmospheric pressure in particular is with inches of mercury, or we can do millimeters of mercury, torr, or atmosphere. And so our atmospheric pressure is usually measured with what we call a barometer. A barometer, as we see here, is where we have a dish filled with mercury and then a tube that's inverted into that dish. Inside the tube is a vacuum. So what'll happen is the mercury will start climbing up the tube till the pressure exerted by the weight of the mercury equals the atmospheric pressure on the outside. So when we're using our barometer and we're measuring the height of the mercury column, around sea level, it tends to be around 760 millimeters of mercury. This is our sea level atmospheric pressure. So that means the height of the column has to go up 760 millimeters before the weight and the pressure the mercury exerts on itself is going to be the same as the air pressure on the outside. Now, if we were to use our Mount Everest example again, Mount Everest has an atmospheric pressure of 253 millimeters of mercury. So for a barometer of Mount Everest, the height of our column will only go up 253 millimeters before the weight the mercury exerts is the same, and the pressure the mercury exerts is the same as the pressure that the atmosphere exerts on our dish. So you can see why humans can't survive at the height of Mount Everest. It's not even half the atmospheric pressure that we have at sea level. And the highest human settlements are around 15,000 feet. So that's still pretty far up there. So now I'm sure when you're asking yourself, why are we using mercury? Mercury is toxic. Well, mercury is very dense. And since mercury is so dense, the height of the column becomes reasonable to read. And mercury is the only metal that's liquid, so that's one reason why they started using it. If we were to use water, we can actually calculate what the height of the column would be using water. And for that, we can compare the different heights using the height of the water column divided by the height of the mercury equals the density of mercury divided by the density of water. And so if we were to do this calculation, and I want to figure out the height of my water column, so I'd have height of water column equals density of mercury divided by density of water times the height of mercury. So that means when we calculate, we have 13.6 grams per cubic centimeter of mercury divided by 1 gram per cubic centimeter for water, multiplied by the height of our mercury column. We're going to use our standard atmospheric pressure at sea level, the 760 millimeters of mercury. So it'd be 760 millimeters. Which gives us a height of our water column of 10,336 millimeters. That's a pretty big difference for our column there, right? Which means the height of our water column ends up being about 10 meters tall. That's a little cumbersome to read. That's one reason why we use mercury, is it's only 76 centimeters tall, or 760 millimeters. Another way we can measure gas pressure is to use a manometer. Manometers are devices that we use when we're determining a gas pressure inside a system. And so what'll happen is the gas inside our flask is going to push the mercury up and down. So the more gas in this flask, the more the mercury is going to get pushed up and down. So you can see if we put gas in it, it pushes the mercury, which causes this side to rise. And we can also, and this would be an example of a closed manometer. An open manometer is where this end is open to the atmosphere. So what'll happen when we add our gas, that'll start to push the mercury down, but the pressure from the atmosphere is going to start to resist that. So we have to take that pressure from the atmosphere into account when we look at an open manometer. So that means the pressure of our gas equals the pressure of the atmosphere minus the change in the height of that mercury column. When we're using closed manometers, we only look at the height of the mercury column. We don't have to worry about the pressure of the atmosphere because this side is a vacuum. Now let's practice this. Let's say a geochemist heats up a limestone sample and collects the CO2 that's released. And he collects it inside a container with an open-ended manometer. After the system comes to room temperature, the height of the mercury column is 291.4 millimeters of mercury. What is the pressure of the CO2 in torr, atmosphere, and kilopascals? Well, since the manometer is a closed system, it's the closed end manometer, that means we only have to worry about delta H. So that means the pressure of our gas equals delta H. And that's all it equals. So that means when we want to figure out a problem like this, since we know it's closed manometer, all we have to look at delta H. That's the 291.4 millimeters of mercury. And remember, the pressure of the gas for an open one, that's going to be pressure of the atmosphere minus delta H. So we have our 291.4 millimeters of mercury. And then I want to convert it into torr. I know for every 1 millimeter of mercury, I have 1 torr. So that's going to give us 291.4 torr. That's the easy one. So then we also have a 291.4 millimeters of mercury. And then we're going to be converting it to atmospheres. So 1 atmosphere equals 760 millimeters of mercury, or 760 torr. So when we do that conversion, we get 0.38. So we get 0.3834 atmospheres. And then we have an easy conversion between atmospheres to kilopascals, so we're going to use that. So my 0.3834 atmospheres, that equals 101.325 kilopascals, which gives us 38.85 kilopascals. So we can measure our gas pressure and figure out any of these units that we want. And so now you guys should be a little more familiar with the idea of gases, gas pressure, how to use the gas pressure units, and also how we measure gas pressure using a barometer and a manometer.